Let's discuss question number 37 from test 3. This is from strength of materials, deflection of beams. You have cantilever beam, you have applied a load, you have applied a moment. So let's break this problem into two. Basically, I'm just flipping the sides. So you applied a load plus you have applied a moment at the free end. So let's solve each of the problems separately and then combine the result. So the basic equation in the deflection of beam is this: m is equal to ei d square y by dx square, where m is bending moment at a distance x. So let's take the first case first. So x here, okay, so this distance is L minus x. So bending moment at this point, because the load P is P into L minus x, so P into L minus x is equal to ei d square y by dx square. That ei comes here. Now I need to, P is constant, I need to just integrate this twice. So let's first integrate this. I'll get minus P minus L minus x square by 2 ei plus some constant, this is dy by dx. Then again if I integrate, I'll get L minus x whole cube by 3 ei. The minus will get cancelled, minus into minus plus 1, so c1x plus c2 is 5. Okay, so now at boundary conditions, I need two boundary conditions. So at x equal to 0, y is 0. At x equal to 0, the slope is 0, so dy by x is 0. So if, because it's a cantilever beam, so when I put these two conditions, let's say the first condition here, c1 y at x0, okay, so this will be pl cube by 3ei and y will be 0, so your c2 should be so when I put x0 y0, I get pl cube by 3ei plus c2 is equal to 0, the first equation. And when I put in this equation the second boundary condition, and this in the second boundary condition, so at x is equal to 0, it's minus p l square by 2 ei plus c1 is equal to 0. So I get c1 c2 from this, and when I substitute back these two in the final equation, I get pl minus x whole cube. Basically I am interested in the slope, so I want this expression. Let's substitute only c1, so minus pl minus x whole square by 2 ei plus c1 is pl square by 2 ei is equal to your slope dy by dx. So at the free end, that is at x equal to L, my slope will be, this term will be 0, slope will be pl square by 2 ei. So this is my slope only when the load is applied. Okay, now let's do the same exercise for this. M is a free end, so when I apply this, the bending moment at any cross section x, bending moment will be m. Just take the right hand side balance, the bending moment has to be, so at this cross section if I take the entire right hand side, moment m is applied, so the bending moment here has to be m everywhere. So the bending moment is constant throughout, so we need to just integrate this. M by ei is d square by dx square, so that is d square by dx square. Now if I integrate this, I get m by ei x plus c1 is dy by dx, and then again if I integrate, it's m by ei x square by 2 plus c1x plus c2 is equal to y. Okay, so again the same set of boundary condition. At x equal to 0, y is 0, so when x is 0, c2 is 0 because y is 0. And now when I substitute the second condition here, when x is 0 divided by x, so I get c1 0. So finally these two boundary conditions substitute in these two, I get c1 0. So the slope equation is this: dy by dx is m by ei x. So at x is equal to free end, that is that I need to find the slope at free end. So at x equal to L, the free end, the slope is dy by dx, that is ml by ei, ml by ei. So let's see ml by ei. Okay, so that is the option. So now by superposition for the given problem, the slope will be, when both the loadings are applied simultaneously, the slope will be slope for the load plus slope for the moment, and that will be your PL square by 2EI plus ML by EI. Okay, so the option is D. Thank you.